K-1, we're going to do independent and dependent events. What's really nice about this is because we're doing advanced probability, if Unit J was hard for you, if you looked at your test score and you're like, woof, that did not go well. Okay, this is kind of a nice chapter because we're going to go over some of those things that we talked about in Unit J, and it's going to make it feel easier. Okay? All right, Zach, you ready? All right. So, independent. What does it mean to be independent? Good. Do stuff by yourself. If we do independent reading in class, what does that look like? Yeah, we're all reading by ourselves. Good. So independent means kind of by yourself, and this means that we have 2 or more events that do not change each other's outcome. There wasn't supposed to be a period here. That was an accident, so you can cross that period out. But 2 or more events that do not change each other's outcome. They're a little bit separate. So if you think about the type of shoes you put on today and the score you get on a math test, does your math test change depending on what shoes you picked out?
Yeah.
What? I look at your shoes and I'm like, Blake chose to wear Crocs today. He gets a 0. No, those things are 2 different ideas. They don't change. They don't have an effect on each other. Okay. So when we find the probability of both of those things happening, we do our probability of the first event, probability of A, times our probability of B. Remember that capital P stands for probability of. We don't like to say P of A, P of B. We want to try and keep those separate. Okay, if you want to write multiply next to this so you remind yourself what that times means or that little dot, our goal is to multiply. Now, as we work on the second one, it's very similar, but it's going to be a little bit different. All right, so as we take a look at this one, dependent. What does it mean to be dependent? What does it mean to depend on someone? Yeah, like to need them to align. What did you say? Align with them? Yeah, align with them. So tax season is coming up. Most of you will be claimed as dependents because most of you somebody else generally pays for where you live. They generally pay for most of your groceries. They generally pay for most of like your school supplies. Not always, but for most of us, we'll be claimed as dependents because we depend on someone. We need someone else. So dependent means that the first event changes the second event, the outcome of the second. The first event changes the outcome of the second event. So a couple things that we like to think about that is if I do my math homework. If I do my math homework, I do my math notes. Generally speaking, how should my test turn out?
Good.
Better. If I don't do my math homework, I don't do my notes, I don't pay attention, that changes the outcome of my test. My test is not so great. All right, so probability of A and B, it's very similar, but it's going to look a little bit different. We do probability of A times and then we write this as probability of B after A. So because there was a change, when we find probability of B, it won't be just like if we did B first. It's going to change. We'll do probability of B after A. Zach, it's amazing when you're gone that like no one talks during notes, and then when you're here, lots of people talk. Probability of B after A. We should say after A happens, I suppose. Sorry. So when we read each of these problems, the first thing we're going to decide is if it's independent or dependent, and then we'll actually find the probabilities. All right, so for number 1 here, it says you roll a dice and pick a card. So if I'm thinking about picking a card from a deck, and I'm rolling a dice. I don't know where my dice went. Does my dice change the cards that are in my deck? No, when I roll the dice, does my deck of cards magically change? No, they're different. They're separate. So because they're separate and they're different, are they going to be independent or dependent? Independent. They're completely separate. They don't change. So our answer for the first part is independent. I'm going to write this kind of on the right side because that's where we'll write all of our answers. All right, first thing we're going to do is find the probability of each of these. So I'm going to find the probability of rolling an odd number. So when I roll a dice, what are my options?
1, 2, 3, 4, 5, 6.
Good. 1, 2, 3, 4, 5, 6. There's 6 total. Which numbers are odd?
1, 3,
And 5. Good. All right, so rolling a dice, we have 1, 2, 3, 4, 5, 6. If you need to write that. And then odd is skip counting, but we start at 1. So 1, 3, and 5. So I'm going to find the probability of my odd first. On my dice, how many odd numbers are there? 3 out of 6. Or we could say that fraction as half. Half the numbers are odd. All right, next up we have a probability of the second part, which is drawing not a heart. When we see that draw always indicates that we're talking about cards, a deck of cards. So if that's not something that you're familiar with, we're not drawing, like I'm not telling you pick up your whiteboards and draw a picture, and then let's see how many hearts are made. When we say draw, we're talking about cards. The playing cards. Jacks, queens, kings. Alright, so over here we have this as our acre chart. So we have kings, queens, jacks, tens, nines, and then hearts is one of the shapes. We call the shapes suits. How many hearts are there? 13. There's 13 of each. Alright, can you look at this? Alright, so all of these, all the way from ace of hearts, all the way down to the hearts, there's 13 of each. But I want not hearts. So which ones are not hearts? The others. Spades, diamonds, clubs. So how many would this be? 13, 13, and 13 would make 39. So there's 39 cards that are not hearts. Out of how many cards total? 52. Now we can simplify that. Another way we could have thought about it, instead of counting the actual cards, is we can look at our suits. How many suits are there in a deck of cards? How many shapes? There's 4 different shapes. There's diamonds, hearts, clubs, and spades. And how many of those shapes are not hearts? 3. So we could have done it that way. 3 out of 4 are not hearts, or that's the way it simplifies. So to find the probability of both of these happening, we're not just looking for the probability of an odd number, we're not looking just for a probability of not getting a heart. We want both of these things happening together. We have that and. Okay, so to do that, we take our probabilities and we multiply. So we're going to take 1/2. That's our probability of our odd. And we're going to multiply it by our probability of not a heart, which was 3/4. Now when we multiply fractions, we can just multiply straight across. So 1 times 3 is 3. 2 times 4, 8. Doesn't work that way when we add and subtract, but when we multiply, we can. Okay, throw that into Desmos. 3 divided by 8. We get 0.375. Which then as a percent would be good, 37.5%. So in your quick check today and in your practice tomorrow we'll actually pause and practice already. The first thing that we'll have to decide is if it's independent or dependent. And then we find the probability of each thing happening, and either we multiply, and then we multiply those. All right, we got 3 more problems. It's kind of a lot of problems today, but they're all a little bit different with the way that they're worded, so it's important we talk about each one. So number 2 says you draw 1 card from a deck and set it aside. You then draw another card. What is the probability that the first card is a queen and the second card is a 7? So when I look at a deck of cards, if I take a card, here's my deck of cards. I take a card, well, pretend they're all the same color, and I set it aside. Are the same cards now in this deck? Or is it different? Did it change?
It's the same.
If-
Change. It's the same.
If I take a card out, when I take the card out, did it now change?
No. Yeah.
Yeah, because the card, is this card in that deck anymore?
Oh no.
No, so it changed because we took one out. So our key word there is that we pick a card and we set it aside. So because we set it aside, we're not putting it back in. That deck is no longer the same. It changed. So if it changed, is that independent or dependent? Dependent means change. You'll be fun away. Okay, that set it aside makes it dependent because it's changing as we go. All right, so to start off with, we're going to find our probability of a queen. That's our first event, our first thing we're looking for. So again, when we take a look at our cards, if we look at an individual, cards, we look horizontally, how many queens are there in the deck? 4. There's 4 of each when we go horizontal. So there's 4 queens. Queen of hearts, queen of spades, queen of diamonds, queen of clubs. Out of how many cards total? 52. Now, we're going to imagine we took that queen. It's now out. The queen is no longer there. One of those queens. We don't know which one. We took a queen out. So now when I look at 7s, how many 7s are there in the deck? Yeah, there's still 4 7s. Did we take a 7 out? No, we took out a queen. But because we took a queen out, how many cards are now in the deck? Yeah, now there's only 51 cards because we took one of those queens out. So that's what makes that dependent. That's what changed, is that it's now over 51. Okay, that's what makes it dependent, is that the amount changed. It went from 52 cards, but we took one card out, so now it's out of 51. So now we take those and we multiply. So our queen was 4 out of 52 times our probability of a 7, which changed because we took a queen out. There's still 4 7s, but without that queen, there's only 51 cards. I don't know why I wrote that 4 so far up. All right, throw that in our calculator. 4 over 52 times 4 over 51. Now we said originally you can multiply across, and when I'm looking at this it says 4 times 4 is 4. What's 4 times 4? 16. Why is my calculator saying it's 4?
Because
Good. The calculator simplified it.
Oh.
So it got a different number. It got 16 over 52 times 51 isn't 663. That would be something else. And then it simplifies it for you.
Okay, so I originally simplified it.
Yeah. So the calculator simplifies it. That way we don't have to do that extra step. So it makes it a little bit easier for us. So 4 out of 663. But if you're using that way as a way to check yourself, you might be like, what? 4 times 4 is not 4. Okay. All right, as a decimal, we get 0.006. Do I want to keep that 6 or change it to a 7? Good. The next number is a 0, so keep it. 0.006. Which can be a little challenging to make a percent. So remember, you can always type that in and do times 100. So 0.006 times 100. I get 0.6%, so less than a 1% chance. So does that make this certain, likely, even chance, unlikely, or impossible? Unlikely, really unlikely, almost impossible. Which again is why poker and any of those gambling games is really fun for some people, because it's all based on probability. Especially, so this is like Texas Hold'em where you pick 2 cards, right? When you pick a card, you're not putting it back in the deck, you're picking another card. And that's where you're kind of deciding whether or not you should bet a lot or not a lot, because it's dependent. In this one, normally a queen and a 7 wouldn't get you very much in Texas Hold'em. That's only 17 for those of you that play that. All right, number 3, you guys are doing great. So first thing we need to think of when we imagine this situation is we're deciding if this is independent or dependent. Is it changing as we go, or is it staying the same? So it says PBIS is giving out prizes for good attendance. A prize box has 4 pop sockets, those things that go on the back of the phones. Those are getting old now. Not a lot of people use them, right? Do you guys still use those? I need one. I have 2 small hands. All right, so 4 pop sockets, 2 AirPods, and 3 free parking permits. 3 prizes are randomly drawn from the box and handed out. Find the probability of drawing a pop socket, a parking permit, and then another pop socket. So is this going to be independent? The box isn't changing as we go. Or is it dependent? The box changes as we go. It changes. Why does it change? Yeah, we're taking stuff out. The 3 prizes are randomly drawn. Are we putting them back in? Like when we look at it, we're like, okay, Camille won a prize. Let's pull it out. Oh, she gets a pop socket, but then we just put it back?
I would put it back.
You would put it back. Okay, but when we take those prizes, we then hand them out. So they're not going back into that box. We're giving them away, and that box doesn't just magically replenish itself. We're going to run out of prizes eventually. All right, so we're going to start with finding the probability of a pop socket. I'm going to do a pop S for pop socket. No, I did the same color. Oh, I'm sorry, I forgot to write. So because it changes, is that independent or dependent? Dependent. And I just did the same color because that was the color we used last time. So it's going to change. So as we go, the first one will be normal, but after the first one, it's going to change. So we got to keep that in mind. All right, so pop sockets. How many pop sockets are in the prize box? 4. Oh, we got to figure out of how many. So we got to figure out how many things are in that box. What's our sample spot space? So we have 4 pop sockets, 2 AirPods, so plus 2, plus 3 parking passes. So together that's 9. Okay, so there's 9 things in the box. Sometimes you got to take that moment to do that extra step of adding. Normally most people would do that in their heads, but because it's our notes, we want to make sure we know where everything's coming from. All right, we're going to now multiply that by finding our parking permits. So there was 4 pop sockets out of 9 things in the box. How many parking permits are there? 3 out of, we're Remember, this is the part where it's dependent. So this is going to change. We gave away a pop socket. So now there's only 8 things in the box. A pop socket is gone. So there's only 8. And then it says, and then another pop socket. So we did pop socket, parking permit, another pop socket. So I'm going to do pop S again for that. But remember, it's dependent. This thing is changing as we go. So how many pop sockets are now in this bin after we gave away 1? Yeah, there's only 3. Out of how many things total now? 7, because we took away 2 of them already. Crushed it. And then we just throw that in our calculator and multiply. Again, Desmos is really nice because then we can see what we're multiplying. So 4 over 9 times 3 over 8 times 3 over 7. Now, in your quick check today, it's going to ask you for your fraction, and then it'll say simplified fraction. If you use Desmos to multiply, you'll just get the simplified fraction right away, and you'll just write it 2 times. Okay? If you're doing it in your head, you would do 4 times 3 is 12, times 3 is 36, and then you have to find the bottom. And you get a different number, and then you would simplify it for the bottom. So we get 1 out of 14. So as a decimal, we get 0. Let's do 3 decimal places today. So 071 or 072. Good, 071, so 0.071. In order to do a percent, we can either multiply it by 100, or we think about moving that decimal over 2 spaces. So if I move it over 1, 2, it would be between 7 and 1, so 7.1%. All right, last problem. You guys are crushing this. Really big part of today is visualizing what this looks like, imagining it. If you need to actually draw it out, or pretend that you're doing it. All right, number 4 says at golf practice. Golf is a spring sport. Any of you guys doing spring sports this spring? Track, softball, baseball, tennis, lacrosse? Anyone? What? You're going to do lacrosse? Should. It'd be fun. Lacrosse? It's like the sticks, and then there's the little ball. There's the little net sticks, and you throw them. You wear hockey gear almost, but it's on a field. It's goofy. All right, here we go. At golf practice, Naima has a bucket of golf balls, 7 yellow, 10 pink, 9 orange. Refocus. Ayan picks one randomly to play each hole, then puts it back in her bucket and chooses another. What is the probability she will only use pink balls for 5 holes? So, as I think about my golf bucket full of golf balls, is that bucket changing in between each hole or not changing? It's not changing?
Your face is hard to tell.
I know. Why is it not changing? She puts it back. So I'm going to switch my highlighters here because this one's independent. She puts it back. So she plays with that golf ball, but then after she's done with that hole, she puts it back. So it's like the golf bin has not changed. So because I put it back, is this independent or dependent? Independent. It does not change. So the amount of golf balls doesn't change. And it's like we're resetting that bucket in between every time. All right, so I want to know pink golf balls for 5 holes. So how many pink golf balls do I have? Out of? Oh, we got to figure that out. Out of 7 yellow, 10 pink, 9 orange. 7 plus 10 plus 9. What'd you get? 26. I was going to say 16, so good job on that one. I missed the 10. I just did 7 plus 9. So 10 out of 26. This would be for my first hole. And how many holes are we doing this for? 5. So now for my second hole, she played with that pink golf ball. She puts the pink golf ball back. How many pink golf balls are there now in the bucket? Yeah, there's still 10 out of 26. And we're doing this how many times? 5 times. Because it's independent, that amount isn't changing. The top amount might have changed if we said pink and then orange and then yellow and then pink and then orange. But in this case, we're just doing pink, 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 pink. Now, if we want to think smarter, not harder, in our calculator, rather than typing that in 5 times, how else could I put it into my calculator? Good, to the power of 5. All right, we get this crazy fraction. You guys ready? Can I cover that up? 3,125 over 371,293. That fraction to me doesn't make a lot of sense. The last one, 1 out of 14, makes sense to me. Like 1 out of every 14 times, it'll work. This one, like, it'll work 3,125 times out of every 371,293 times. So this one, for sure, that percent is going to be a lot easier to work with, or the decimal. So we get 0.008. When we round, do we keep it at the 8 or do we change it to a 9? Yeah, keep it. So 0.008. And is that going to be 88 or 0.8%? It's going to be 0.8%. When we move that decimal over 2 times, it stops right in front of that 8. So 0.8%. Which to me is kind of interesting because each time we take that pink ball out, there's more pink balls than any other colors. So to me it feels like that should happen more often, right? The majority of the most of one color is pink. But to get 5 pink balls in a row is less than a 1% chance. Kind of crazy? Not crazy? Does anyone else's brain, that makes their brain hurt? Math just makes your brain hurt? Yeah, me too.